Hello, I am Dr. Sigar Kanti, Associate Professor of Mathematics, Government First Year College, KR from Bangalore. In this video, I am going to prove some results on trees. Result 1, if T is a PQ tree, then T is acyclic and P equal to Q plus 1, or we write Q is equal to P minus 1, right? So to prove this, we prove the result by induction on the vertices. First one, what is given here? T is a PQ tree, right? Then we have to prove that then T is acyclic, and we have to prove that P equal to Q plus 1. If T is a tree, then by the definition it is acyclic. Then no need to prove this acyclic. This is in the definition. So here first I'll write, since T is a tree, this implies T is acyclic. Now we have to prove that P equal to Q plus 1. So that is here. To prove that P equal to Q plus 1, we prove this by mathematical induction. Induction on P, that is the number of vertices. Now here if P equal to say 2, then so this is our graph, and here we have P equal to 2, Q equal to 1. This implies P equal to Q plus 1 or Q equal to P minus 1. That is the result is true for P equal to 2. So that is the result is true for P equal to 2. Now we assume that the result is true for all trees with less than P vertices. So that is here. Assume that the result is true for all trees with less than P vertices. Okay, this is our assumption. The result is true for all trees with less than P vertices. Now let me consider a tree with P vertices. So that is here. Let T be a tree with say P vertices. Okay, T be a tree with P vertices. Now let E be an edge of a tree. We have considered this tree is a tree with P vertices. Let E be an edge of the tree T. Then T minus E is disconnected and has exactly two components, say T1 and T2. This is because every edge in a tree is a bridge. So that if we consider any tree here, this is a tree. Okay, this is a tree. Now if we remove any edge here, suppose if I remove this edge, right, then what happens? this part is one tree and the remaining part is another tree. So that is here we get exactly two trees in t minus e. And here suppose this is our t1 and this is our t2. Okay. Now what is this T1? T1 is a tree with less than p vertices and T2 is a tree with less than p vertices. Now let me consider T1 is a tree with p1 vertices and q1 edges. T2 is a tree with p2 vertices and q2 edges. Then number of vertices in T1, that is p1, plus number of vertices in T2, that is P2, is nothing but total number of vertices in T. That is here P1 plus P2 is equal to P. And if we have Q1 edges here in T1, Q2 edges in T2, then Q1 plus Q2 is equal to total number of edges minus 1. Okay, so that is here two components T1 and T2. Let T1 be a P1 Q1 tree and T2 be a P2 Q2 tree, and here P1 and P2 are always less than or equal to P. Okay, and here P1 plus P2 is equal to P and Q1 plus Q2 is equal to Q1 plus Q2 is equal to total number of edges minus 1. Okay. And here since T1 and T2 are two trees with less than p vertices, therefore by assumption the result is true. So that is here we can write P1 equal to Q1 plus 1 and P2 equal to Q2 plus 1. So that is here since T1 and T2 are trees with less than p vertices by assumption P1 equal to Q1 plus 1 and P2 equal to Q2 plus 1. Okay. So therefore here we have P equal to, therefore P equal to P1 plus P2, this is equal to P1 is Q1 plus 1 plus P2 equal to Q2 plus 1. So this is equal to Q1 plus Q2 plus 2. So that is P equal to, but here Q1 plus Q2 equal to Q minus 1. Okay. So that is here, this is our Q minus 1 plus 2. So that is, this implies P equal to Q plus 1. So therefore by mathematical induction the result is true for all trees. Okay. Therefore by mathematical induction the result is true for all trees, right? Next I will go to another example, another theorem. If a PQ graph G is a cyclic and P equal to Q plus 1, then G is a tree. Okay. So here suppose G is a PQ graph. If G is acyclic, that is having no cycles. And if we have P equal to Q plus 1, then G is a tree. So to prove that G is a tree, what I have to prove here is, we have to prove that G is connected, first one connected, then and it is acyclic, that is connected acyclic graph is a tree. So here it is given that a PQ graph G is acyclic. Acyclic is given here. Okay. Only thing I have to prove that this graph is connected. So connected means G has exactly one component. So to prove that, suppose G has a k components. Okay, then either I will get a contradiction or I will prove that k equal to 1. Okay, so that is here. To prove this, G is a cyclic. This is given. This is given. So just we have to prove that. We have to prove that. We have to prove that G is connected. Just if you prove that G is connected, then we can say that G is a tree. And this thing is given here. That is P equal to Q plus 1 is given. So using this, we try to prove that G is connected. Okay. Now here let me assume that. So that is here. Let G has say k components. K components G1, G2, G3. So G and GK. Okay. GK. And that is here, G has k components means G1 is acyclic and this is connected. G2 is acyclic connected. G3 is acyclic connected. GK is acyclic and connected. That means here each Gi is a tree. So that is here G has k components. Each Gi is a tree. Okay. Now let Gi be a PIQI tree. Okay, so that is here. G1 is a P1 Q1 tree. G2 is a P2 Q2 tree. G3 is a P3 Q3 tree. GK is a PK QK tree. Right? And here we have P1 plus P2 plus P3 plus P4 up to PK is nothing but number of vertices of G, that is equal to P, and number of edges Q1 plus Q2 plus Q3 up to Qk is nothing but number of edges in G. Okay, that is Q1 plus Q2 plus Q3 up to Qk is equal to Q, and P1 plus P2 plus P3 up to Pk is equal to P. So therefore here we write P1 plus P2 plus P3 plus up to Pk is equal to P, and Q1 plus Q2 plus Q3 plus Qk is nothing but this is equal to Q. Okay. Now given that we have each Gi is a tree. Each Gi is a tree. Therefore, Pi equal to Qi plus 1. So that is here we write P equal to P1 plus P2 plus P3 plus up to Pk. This is equal to Q1 plus 1 plus Q2 plus 1 plus up to Qk plus 1. So this is equal to Q1 plus Q2 plus Q3 up to Qk. This is equal to Q1 plus Q2 plus Qk plus 1 plus 1 plus 1 plus k times. This is equal to k. Okay. So that is here we are getting P equal to Q1 plus Q2 up to Qk is nothing but Q plus k. But what is this P? P is equal to Q plus 1. Okay, we have P equal to Q plus 1, right? So that is here this P equal to Q plus 1, which is equal to Q plus k. What this implies here is k equal to 1. So what we have taken this k? K is nothing but the number of components of G. So this has only one component. That means this implies G is connected. Okay, G is connected. So that is here. G is acyclic and G is connected. Therefore, we write G is a tree. Okay, G is a tree. Next example, next one more result. And here if I combine these two results, that is here, yeah, this result, if PQ graph G is acyclic and P equal to Q plus 1, then G is a tree. And previous result, if T is a PQ tree, then T is acyclic. Combining these two, we can write. So here, combining the previous two results, we can write a characterization, that is if find only if. Okay, so how can we write is like this, we can write a PQ graph, G is a tree, if and only if G is acyclic, G is acyclic and P equal to Q plus 1. So combining these two rules, we can write a PQ graph G is a tree if and only if G is acyclic and P equal to Q plus 1. Okay. Next, I will go to one more result. It is a very non-trivial tree. Every non-trivial tree has at least two end vertices. At least two end vertices. Okay. So here non-trivial, P greater than or equal to 2. Now here we can verify this result. Suppose G has only two vertices. Then this is the end vertex, this is another end vertex. Suppose we have three vertices tree. This is one end vertex, this is another end vertex. Okay. And next, sorry. Okay. So that is if G is a tree with three vertices, then here we have this one end vertex, the other end vertex. If you write any trees here, yeah, this is a tree. Here we have 1, 2, 3, 4, 5, 6. 6 end vertices are here. So that means here we can observe that by drawing the trees, we have at least two end vertices. We have to prove this. For that, what I do here is, first I will consider, suppose G has no end vertices, means each vertex is of degree greater than or equal to 2. And then we consider G has exactly one end vertex. Okay, so one vertex is of degree 1 and remaining all other vertices have degree greater than or equal to 2. Okay, and then we get some contradiction there. So then we assume that G has exactly at least two end vertices. So to prove this, what I do here is, so here to prove this, I'll go like this. Let T be a tree with P vertices and Q edges. Okay, P vertices and Q edges. Let T be a PQ tree. And we know that if T is a tree, then here we have P equal to Q plus 1, or we write Q equal to P minus 1. This we know. If T is a tree, then this equation is satisfied. So what I have to prove here is T has at least 2 end vertices. Now here, if possible, or we consider case 1, suppose T has no end vertices. Okay, suppose T has no end vertices, then what happens? Degree of each vertex is greater than or equal to 2. Okay, then what is the sum of the degrees? Sum of the degrees greater than or equal to total P number of vertices are there, and degree of each vertex is greater than or equal to 2. Therefore, sum of the degrees is greater than or equal to 2P. Okay. Now, what is the sum of the degrees? It is nothing but twice the number of edges. 2Q is greater than or equal to 2P. This implies Q is greater than or equal to P. Q is greater than or equal to P. So that is here, this implies Q is greater than, we write P minus 1. Okay, greater than or equal to P, therefore greater than P minus 1. This is a contradiction here, which is a contradiction. So therefore, this possibility is not there. That is no end vertices. That means at least one end vertex is there. Now again we consider another case here. Case 2. Let G has exactly one end vertex. So that is out of P vertices, one vertex is of degree 1, and the remaining all other P minus 1 vertices have degree greater than or equal to 2. So that is, again we write here, sum of the degrees greater than or equal to P minus 1 vertices have degree at least 2. So therefore, greater than or equal to 2 into P minus 1 plus 1 vertex is of degree 1. So that is plus 1. But what is this sum of the degrees? This is nothing but 2Q. That is, left hand side is 2Q greater than or equal to, what is the right hand side? 2P minus 2 plus 1 greater than or equal to 2P minus 2 plus 1. Okay, that is here 2Q greater than or equal to 2P minus 1. And this implies, dividing throughout by 2, we get Q greater than or equal to P minus 1 by 2. So that is, this implies Q is greater than, again I am getting Q greater than or equal to P minus 1 by 2 means must be greater than P minus 1. Again, this is a contradiction. So again, this is a contradiction. So therefore, T has at least 2 end vertices. That is here, every tree has at least 2 end vertices. Okay, thank you. I will stop here.